Hello, it's great to be here today. We're going to present, along with my colleague Deniz here, one of the new SDV projects, Eclipse Software Defined Vehicles projects called Eclipse Muto. Eclipse Muto is born out of our work for a product that we used for building low-speed autonomy solutions. It's basically a stack that we use to manage the software that was running on the device, and we thought this would be useful for others, so we decided to open source. It does not include algorithms or other things, but it allows you to basically manage the software that's running on that device. So I'll just try to give you a quick update on the project, what's happening, and we're slowly putting out some of the sources out there, and hoping to have our first release in the first quarter of 2023. Just very quickly, our project lead and lead engineer Deniz is here. I'll be doing the talk, but if you have other technical questions, we'll be available here for the rest of the week. You can always approach us in the rooms. Just to give you an idea of what the Composer product is, it is for being able to switch the ROS software that's running on a device after it passes certain gate checks and switching some of the nodes off and turning some of the nodes on in the ROS graph and doing this adaptively through some machine learning algorithms. And this means that if you have a set of application components that are running to solve one problem, and if you sense that you are in an environment that these conditions no further apply, you can use Muto to make the switch from one set of software components to the other one. You can do this when, in some cases, when your device is running, so it can be done in real time. In other cases, it may require, for example, the device to come to a full stop, do the switch, and start again. So, basically, this is a very high-level diagram that we use to describe what components there are in Muto. There are pieces that run on the device. They require ROS to be present. So these are the components we call agent, which is basically a gateway, an edge gateway, and the composer, which does this adaptive orchestration using ROS concepts. And to manage what's happening with these adaptive stack that's running on the device, I've used the digital twins on the cloud, and a dashboard and other services allow you to monitor, do some telemetry, and also send commands to the device using this gateway. So primarily, the source that the code that we started putting up into the GitHub, you'll find that among other ones, you'll find the edge gateway code, which is the Muto Agent. There's the Muto Composer and the Muto Dashboard that is used to manage these components. We understand the fact that you cannot have one solution and one set of components that answers everybody's needs. So the idea with all these software pieces that they provide extensible plugin points where you can extend their capability for whatever commands that you want to add or replace, how the Muto examples do this for you. So Muto comes with example plugins for commands, telemetry, and composition on the device. But basically, these are examples on how you can use Muto to build your own management stack. The typical sort of the command plugins that we're talking about, for example, they can be for ROS monitoring. People who are using ROS are very familiar with the ROS CLIs. For example, they can say ROS node list, ROS node info, topic list, whatever. So the edge gateway ROS command, we have an example set of plugins that extends the CLI to the cloud. So you can, you don't have to be on the device to run these commands. You can just do it over the dashboard. Or we have some telemetry plugins. Again, it's very common for a developer when working with ROS to do ROS topic introspection or doing echoes or publishing messages onto the ROS topics. With the telemetry, you can, and the rate that these messages can be happening at the blinding speed. So with telemetry, for example, you can do filtering on some of the ROS topic echo and push this onto the cloud through the digital twins part. These are all just examples of what you can do. Also, Muto Agent currently is, it comes with a twin adapter that works with Eclipse Ditto, which is one of the Eclipse IoT projects. It's a great set of tools that gives you REST APIs for managing things, they call, on the cloud. But it also has a communication stack which allows you to talk to the device through asynchronous channels like MQTT or REST or any other protocol. So it's a great one to start, but it's not the only one that you need to use. The composer where most of this thing happens is basically it's an orchestrator. It orchestrates the flow of steps, and each step can delegate what it does to a plugin. For example, you can have one thing that I should add, that we have this concept of a model for the ROS nodes that are running on the device. Basically, it's a manifest, a bit like the Kubernetes deployment manifest. So the Muto Composer can introspect the device to see what's running, and then it can take the proposed stack, and it runs it through these steps through the plugins, and each plugin can modify what is going to happen on that device. And at the end, if everything is okay, you can have the final plugin doing the, launch this thing. And of course, you can imagine many different flows and many different steps on how we can do this. So Muto Composer manages that. Dashboard is basically our user interface technology. It's a web interface for very quickly building widgets and controllers and telemetry, whatever, to access these capabilities that are running on the device. So basically what, on a sort of high level, the challenges that Muto is trying to, when I get it close, it's a different, anyway, sound for me. The challenges that we find in building these systems is when you are working with ROS, you create a setup and you prepare your device with the setup, then it's very hard to without completely changing the installation, modify what's running on the device or get someone else started. So it's a static environment that is prepared to run a specific set of software and components. So the thing that we're trying to address is make this dynamic and live, so be able to manage this through a model definition. The second aspect that we're trying to address is, this is not the part that we have opened up, unfortunately, but we work with an industrial partner with some use cases, as I said, low speed autonomy, that we try to make this contextual. So we have our own flows that uses the Composer technology and our own plugins, which does this contextual adaptation of the ROS stack running on the device. So that's pretty much what Eclipse Muto does. Architecture is pretty simple. It sits on top of the ROS layer. It's basically ROS, Muto technology is ROS nodes. Agent is a ROS node, and Composer is a ROS node. So when you spin this up, the only thing that needs to be on the device at that time is the agent and the Composer. So, of course, you can choose different ways to deploy the software components onto the device. You can use containerized technology, or you can decide you want to pull it from your own private repository, whatever provisioning technology you want to use for those software components. That's a part of the Composer steps that you need to take. Muto will spin up those nodes and will manage, it will have a managed stack that's running on the device that it's responsible for. To control this agent and the Composer behavior, you work with a digital twin. As I said, it currently uses an Eclipse IoT technology, Ditto. To reach the device behind firewalls and security things, it's not, devices are they're not directly connectable, so we use MQTT and a payload that is packaged into MQTT messages that goes from the digital twin onto the device, and also the responses travel through the same mechanism. Also, the device can talk to the digital twin server through a direct REST API if that's available. We are running, we're spinning up 2 learning services that are available, and hopefully they will move on to Eclipse namespaces. We're working with the Eclipse Foundation to give us those names. But one is basically, it's a Ditto for Muto. Ditto has a sandbox that that you can use for learning purposes. So we spin up a clone of the Ditto sandbox just for Muto. It also adds a connectivity layer, which is not available with Ditto sandbox. For obvious reasons, it can get overwhelmed with people using that as a trial bed. This server gets spun up every day. It will forget everything that's on it. And if it gets overwhelmed, it will stop working. So it's just for learning purposes, not a production environment. And the dashboard is basically, every time we push a new capability, a new example, it rebuilds itself and puts itself onto the, again, Azure cloud. So it's available for people who want to see and test their dashboard ideas. You can clone it in your own environment and run it locally too. Let me just follow the time so that we don't run out. I think I talked about this already. Although Ditto is built into Muto's capabilities, it's not a requirement. We have capability to build different twin technologies into Muto. Currently, we don't have a business case for it, so Eclipse Ditto seems to be there for a while. But if your case requires to build onto a different twin technology, you can ask us how to do that, and we'll be more than happy to give you directions. At the heart of the model that we use to make things composable is what we call a stack. It's basically a model that we can dynamically change that supports the ROS constructs like the nodes and parameters and arguments and things like that. And you can store these with the digital twin. All the parameters can be on the cloud. And this is a self-referential, it's a bit like a Kubernetes deployment manifest if you're familiar to but it is a sort of a JSON version of something that is close to the ROS constructs. And basically, you can capture any ROS application using this. It's, I think we are very complete in terms of supporting the ROS constructs. We might be missing some. Any feedback or the use cases that we use so far seems to be handled. What we have done for the Muto project is we're trying to capture everything that we see on the open source that runs a ROS-based system. Autoware has some examples, F110.org has simulations that are running using ROS. So we try to capture as many examples as stacks and put them onto our twin server so people can experience using those algorithms. So we don't do algorithms, but we try to show how we can use Muto, for example, to spin up something that runs those algorithms for that system. So if you can provision them onto your device, it will bring them up and run. I'll hope to show you that with a demo. A bit more detail on the stack. So as you can see that if you're familiar with, for example, ROS launch concepts, that is, some of the parameters that we'd use to identify the ROS package and the executables and the parameters that you have to push into it in order to stop it. Although we support sort of the built-in some of the expressions that are used in ROS, you can also pull these from the digital twin. So those are the additional features that are in place. And of course, when you put them into a digital twin, you can use the security that's provided by the digital twin in terms of who can change and see and modify these assets. The device is basically, it can be a car. It currently follows the model that's provided by Ditto. You can use different information models to capture things that are irrelevant to Muto. But what Muto adds to the digital twin is a section about the stack that it uses. And also, if you add some telemetry features, for example, it will store them with the vehicle definition so that every time you spin up that vehicle, your telemetry specifications are there so you can start and stop them, whatnot, and push them onto a synchronous engine. So a bit more in detail, these are the two nodes that are running on your device to start with. Muto Agent supports the command plugins. These are basically, they run, we support two types of plugins. The plugins that run within the process of the node that you send, for example, some commands, you may want them to just run within the agent process and do their thing, like ROS CLI things, and just respond back. But other commands like maybe the composer, the nodes that are spun up by the composer, you don't want them to run within any of one of those processes, or maybe on that node. So they will be managed by the Muto Composer. It will spin up a process or on a different node and spin those nodes up and run them. As I said, currently we sort of, all of these use different, same plugin concept, but do different things. These are some of the examples that are provided. As I said, we kind of support some ROS CLI commands. We have a simple-minded sort of telemetry thing built into it that you can echo the ROS topics, serialize the ROS messages onto an MQ2T payload, and basically build simple widgets on the cloud to display them. Again, it also supports a way to access the features on that device using asynchronous connection protocol. Basically, this is MQTT to reach the device and also get things out of the device. The composer itself is basically, you can send a definition of a stack to the composer, and although agent receives this command, it basically publishes a message onto the Muto topics. There's some topics that are running specifically for Muto, and the composer basically, the composer listens to this topic and will pick up the definition and will run that flow to execute what is needed to get that thing running. And that may replace whatever is running there with something else. An example of a workflow that can be managed with the plugin, basically, this is sort of inspired by some of the more IT-related concepts like processes and workflows. But it's a very simplified, lightweight engine. It's not like a big BPMN engine that's running with huge overheads. You can sort of identify the steps. You can name them for whatever. And then you can identify which plugins will carry out what steps. You can have compensation nodes and whatnot. And whenever I send a new proposed stack, each one of these nodes will basically can modify what is proposed. So we'll provide also basic graph algebra within Muto. You can take diffs. For example, if something's running on the device, I send a new stack, it will basically introspect the full node graph, including the parameters and arguments, and find out the diffs. And it provides this as an input to the following steps. So you may have to go through some validation and verification steps, and also some provisioning. If there's a node there which is not installed onto the device, what do you do, right? If it's a containerized node, the metadata on the node should be used to install this onto the device, get it running, and verify whatever. And then you can move on to the launch step, which is the simplest thing. Once you know that you can run it, everything is there, and it can be done when the velocity is 0, whatever. This launch node will spin up that graph, and things will start working. This part is sort of the experimental part, if you like. Once something is running on the machine, you don't always have to remote control what's running on that device. You can have deep learning algorithms that use sensor data and also maybe the behavior of the device to decide if you have to make modifications. Let's say some sort of imaginary scenario. You have adaptive cruise control and one of your sensors is not behaving, so you may want to take out the cruise control out, right? So all of this can be done algorithmically too. You can use some kind of a adaptive Muto system to do the same thing. So that's a simple-minded thing, but you can also imagine if you're in a parking lot and you want to get an automated parking scenario running, and each parking lot has a different set of nodes that are certified to run on that device. You can imagine those being provisioned onto the device and being executed for that specific parking area. Okay, so I'm a little running behind. But the whole idea of adaptive stacks is, as I said, we look at this model, the stack model, and there's metadata attached to these stacks in terms of what environments, what hardware, and what kind of conditions that they should be valid for. And then you can use different inputs coming from, let's say, everything that's available on the ROS data bus, to see how we can modify this. And once you decide what the modification is, basically, Composer will take this online for you. But this is not a part of Muto, but this is something that you can achieve with Muto if you had the right algorithms in place. Quickly, this is basically an example dashboard we built. And while we were building this, also we created some libraries that you can add widgets and different types of dashboard to this one. And it also sort of with the whole philosophy of Muto, we want everything to be live. We don't want this to be statically compiled either. So you can basically dynamically assemble the whole user interface on the fly with what we called, with a library called Live UI. And this is basically an example of thing. We also made this one open source. It's available under the GitHub repository. And there are some examples for how to apply this to different types of scenarios, including some mobile apps. It currently supports sort of some native technologies like React and React Native and Vue and native script. So you can use Live UI to build an application using any one of these technologies. And there's a bunch of showcases up on the GitHub too on how you can use this one. I'm going to show you a demo that uses software from a front end. This is basically a learning system, if you want to call it. It's used by some of the universities for teaching autonomous driving algorithms to, I think, fourth-year or master's students. It has a hardware with some sensors on it. It also has a very nicely documented website and assignments on how to build some reactive algorithms or simple pursuit types of things. So we decided, well, it may be a good thing to capture some of this in Muto stacks to show how we can use Muto. I was going to do this live, then I didn't want to tempt fate. So I recorded it about half an hour ago. Let's see if it's... basically, on the left side, you're seeing the Muto dashboard. And on the right, there's a VM running on Ubuntu representing a device. So I just started the system with the agent and composer. And this one will connect to the, I think I click on it, go for it. Okay, so these are basically ROS CLI commands that will run on the machine. For example, when I ask for the nodes, it's to the ROS node list, and then to the ROS node info. So this is basically what you would see from ROS graph. And similarly, it goes and connects to the parameter server that's running. I will go look for, for example, commands that are available on Muto. Basically, if I send a command that has ROS topic, it will run a plugin to get the response. And so it's going to use that to, for example, see what topics are currently out there now. It's just started, so there's nothing running on it. So let's go to some of the stacks that were captured, I think. All right, let's see. F110 simulator, which has this ROS simulator on it. There is time elastic band available on the ROS repositories that you can very easily download. So what I did is, did I click on it already? So it seems I clicked on it. So it just basically wanted it to launch the time elastic band algorithm. So it has the ROS as a node, so it popped up the ROS. With this algorithm, you can give a global goal, and then it has a local planner. Uses a map and LiDAR. So let's say, for example, let's give it a global goal of putting the car in that direction. And you can also dynamically, now it will set, start the automatic navigation. You can drop, this is just the time elastic band algorithm, so you can drop a dynamic obstacle in front of it, so it will drive around it, whatnot. So what I want to show you is, although this is kind of a fun algorithm to look at, and this kind of a sort of a map, you can see park and whatnot, it's using, for this kind of a loop, if you have used F110 org or one of, this is at MIT Levine building, second floor map or something. So it's the corridors and it's the F110 car. So now it's moving with the time elastic band, but I'm going to switch it to something that's probably a bit more suitable for this kind of a, it will be faster. So there's a reactive algorithm, simple gap follower reactive algorithm. It actually switched to that one. Now it dropped the time elastic band, it's moving with the gap follower. So we asked the device to completely change the different stack. It did the graph algebra around it. And you can see different nodes are probably running now on that device. Okay, you can see the gap follower algorithm. And we can go back and say, oh, okay, I want to switch back to something else. Oh, this part is about the telemetry. For example, those algorithms are putting the Ackermann messages onto a nav topic. So you can see the topic, you can say, echo this. And of course, that's happening with a frequency that's not suitable for pushing out to the cloud. So we choose, send me something every 5 seconds. Don't send me everything else. So, it will open up that. I will open that up and say, start the telemetry now. This basically sends a command now with an action, start the telemetry with some of that spec. And it also providing a topic for MQTT to capture this at. And then you can see the telemetry messages coming in the JSON form from there. Now, not everything is, of course, good to do. If it's in the gap follower and you switch to, from time elastic band to gap follower is probably a safe switch, but from gap follower to time elastic band is not a safe switch. So if you did, switch this back to something else, and if you're in the wrong spot, you can smash the car onto one of the walls. So that is why those flows are important. You have to do some validation and verification of those in terms of switching, what is safe, what is not, what is valid. And I think these are some of the questions. Switched, but I did it right. If I did it somewhere around here, it would have smashed onto the wall. So these kind of switches are really sensitive to the environment, and you have to do a lot of different things. And a different set of things are running. I think I'll speed up a little bit, so this should be the end of the demo. Okay. How do I switch back to the? Okay. Okay. So the website is up. We're updating the documentation so you can do a lot of these yourself very easily. You don't need too much to run these examples. Muto does not require much from the machine or the edge device. Of course, the algorithms that are running have different requirements. So you can try many of these with a very low-cost hardware platform. And currently, as I said, we just joined the SDV group, and there are many projects there with many interesting different technologies. So we're finding it an exciting time for us and a challenge to see how Muto can fit with other projects under SDV, and we hope we can grow with that community. The initial code is already committed there, and there are some preview code releases already out there. I have to admit, you won't be able to probably spin it up yourself, so we'll try to fix that up in the next couple of weeks so that anybody can try what we have shown. And our first sort of a release is planned for the first quarter of 2023. Just sort of quick things to wrap up. For SDV, there's a Hacker Day on Thursday, where all SDV projects will be there along with us, the Muto project. So you can get to meet all of the SDV projects together, and we hope to have technical people and project leads available there to work with each other and also with the wider community if you have other questions. Another exciting event that is happening next month is in Berlin. On November 7th, there's a BCX hackathon, and there's an SDV challenge there, and the following SDV projects are also attending, and we'll be there again to meet our community and other people. So thank you very much. I hope I completed right on time. If there are some questions, I would be very happy to answer. Thank you.
Thank you for your presentation. I would like just to ask, is Muto compatible with ROS 1, ROS 2, or both?
The current one, the current release that you have seen is ROS 1, but we are about to release a ROS 2 adaptation. So our target is ROS 2
Nice.
for
Thank you.
first quarter. Yes.
Thank you.
Any other questions? Okay. Well, we have some Muto stickers, cool Muto stickers, so if you guys want to have some of those, they're around the table. So thank you for attending.